like to thank the organizers for giving me this opportunity to present my work. I'm going to be presenting some work that was published earlier this year, that I had done with David Grabner and my PhD supervisor, Nikolai Gromov at King's College London. I'm also going to present some exciting new results that we have. All right, so let's get to it. So I will describe how we can use the quantum spectral curve, a powerful integrability-based approach to calculate the spectrum of states of the one-dimensional defect CFT that lives on the half BPS Wilson line in n equals 4 supersymmetric angular theory. That was a huge mouthful, so let me unpack the statement. First of all, n equals 4 supersymmetric angular theory is a superconformal field theory in 4 dimensions. And it has with gauge group SUN, it has, in addition to the gluons, it has also 6 adjoint valued scalar fields. And in the limit, in the large n limit, so in the limit that the rank of the gauge group goes to infinity, this theory is integrable. Yeah, I mean, it's a very rich theory and there are many more interesting features, but for our purposes, this would be sufficient. Okay, so in this theory, what we can do is consider the supersymmetric cousin of the Wilson loop called the Maldacena-Wilson loop. And the way you construct a Maldacena-Wilson loop, which is a supersymmetric cousin of the Wilson loop, is you include not just the gauge field in your path ordered exponential, but also you include a coupling to the scalars. So it's a fixed coupling to the scalars represented by this unit vector n. N is just, it points at some direction in this flavor space. So we have an S5 flavor space of the 6 scalars that live in n equals 4. So basically you choose a direction in this flavor space and that defines your scalar coupling. It turns out that if you have a Wilson loop, a Maldacena-Wilson loop, I'll use these terms interchangeably. So it turns out that if you have a Maldacena-Wilson loop in n equals 4 supersymmetric angles theory, which has the shape of an infinite straight line, then it is half BPS, meaning it preserves half of the supersymmetries of the theory, and additionally, the line itself preserves the one-dimensional conformal group, and therefore we can define a defect CFT that lives on this line itself. And yeah, and basically this. So what we're going to do today is we're going to try to study the spectrum of states on this defect CFT. However, before we actually get to the defect CFT itself, we need to take a small detour by considering the cusped Wilson loop in n equals 4 supersymmetric angles theory. The reason we do this is because, well, there are 2 reasons, but the most immediate reason we do this is because the cusped Wilson line, Wilson loop in n equals 4 supersymmetric angles theory is basically where we know how to solve the problem. We know there exists an integrability description for this object. The quantum spectral curve was written down for it, so we start from here. All right, so let's get a bit more quantitative. So consider the following setup. So we have 2 infinite Wilson rays, and they meet at a physical angle phi. So basically, this is an infinite. This line is semi-infinite going till infinite minus infinity. This is semi-infinite going to positive infinity, and we meet. They meet at this physical angle phi. Additionally, so as you can see, we've included a point of non-differentiability in the path, basically by including this cusp. Another thing that we have done is included another point of non-differentiability by basically changing the unit vector in the flavor space. So we change the direction of the scalar coupling, and this is parametrized by an angle theta. So the dot product between these 2 unit vectors is theta, is cos theta. All right. So this is just the setup of a cusped Maldacena-Wilson loop in n equals 4 supersymmetric angles theory, and if you compute the expectation value of this object, it diverges, but it can be renormalized multiplicatively by including what's called the cusp anomalous dimension. Okay, fine. So now, suppose we have an infinite. Okay, yeah, I mean, right, like bear with me for a moment. The setup why I start from here will become clear in a few seconds. So suppose I have an infinite straight Wilson line. I can always make a conformal transformation from this infinite straight Wilson line and make it a circle. All right. If I perform the same conformal transformation on a cusped Wilson line, what I end up getting is a Wilson loop in the shape of a lens, right? I can do the same transformation of a Wilson of a Wilson loop with two cusps, and then I can get, like, well, for lack of better word, a circular triangle, right? A triangle with circular edges. I can do it for n points. Now, the reason this is interesting is because it was shown. So it was shown by these authors for the case of this, the lens-shaped Wilson loop. For these by these authors in the case of a circular triangle-shaped Wilson loop. So these are my supersymmetric Wilson loops, and by this author for like a circular n-gun. So you have a Wilson loop with circular edges and n cusps. So it was, but just for the non-supersymmetric case by this person, that the expectation value of this operator, so the expectation value of a Wilson loop with n cusps, has the same form as that of an endpoint function of local operators in a conformal field theory, specifically in the case of n equals 4 supersymmetric Yang-Mills theory. So this is good because it illustrates our approach in a way. So what one can do additionally is we can consider a setup like this and also make insertions of local operators at these cusps. And again, this was studied by various groups. Has been studied by various groups in different contexts. So we can make insertion of local operators at these cusps and also study endpoint functions of these cusps with operator insertions. But from our point of view, what's important is what we can then do is just take all the cusp angles to 0. And when we do that, we end up on the defect CFT that we are interested in, and we can calculate an endpoint function on the defect CFT itself. What we are going to do is just calculate the 2-point function, because what we're interested in is calculating the spectrum. But in principle, one could calculate higher point functions as well. Okay, so yes. So let me just rephrase that. So our goal is basically to find the non-perturbative spectrum of operators in the defect CFT that lives on this infinite straight half BPS Maldacena Wilson line. And our strategy, as I mentioned just now, is we start with a cusped Wilson line with these operator insertions. This is a situation where we know how to solve the problem, and then we then we take the cusp angles to 0. Like properly, we don't, in a proper scientific way, we take the cusp angles to 0. And by doing this, we can access two types of scalars in the defect CFT itself. The first corresponds to the case where we take both theta, the internal angle, and phi, the physical angle, to 0. In this case, we are just studying scalar insertions on the half BPS line. And in the case that we have finite theta, that means that you have an infinite straight Wilson line, but then at some point, the coupling to the scalar changes. What we can study actually are called defect changing operators in this defect CFT. This was also explored by these authors a couple of years ago. All right. So, yes, since scalar insertions are what we want to study, let's make a bit of a survey about the kind of scalar insertions that we can do, and the kind of techniques that are available, were available, etc., etc. So what we can do. So the first thing that we're going to do is we're going to decompose the space of scalars into a set of scalars that are perpendicular, that are orthogonal to the scalars that couple to the Wilson line, and a subspace of scalars which are spanned by the scalars that couple to the Wilson line. The reason we do this is because until now, the only scalar insertions that were studied from an integrability perspective were those of orthogonal insertions. So you make insertions at the cusp, scalar insertions at the cusp of the Wilson line of those scalars which don't couple to the two Wilson rays. Okay, so the integrability description goes as follows. So you start with cusp Wilson line with an insertion of L orthogonal scalars. For this setup, there was a thermodynamic beta-Ansatz equations written by Nadav from King's College in 2013, and also by Maldacena and friends. I mean, it was written by both these groups, and basically, so they managed to write thermodynamic beta-Ansatz equations for this setup, and then if you take the number of insertions L to 0, the state that it describes actually lets you calculate the cusp anomalous dimension. Now, our method, the quantum spectral curve, was also adapted for this setup by Kolya and Fyodor back in 2016. Okay. All right, this is good, but this is not, so orthogonal insertions, we know how to set, they're brought under the purview of integrability. It's all good, but right now that's not our focus. Our focus are parallel insertions. Now, parallel insertions in general are a bit tricky. First, from a field theory point of view, it's not clear basically what these insertions correspond to, because in principle they could be some combination of these two scalars, or they could even be other scalars involved. So we don't know exactly what these insertions correspond to themselves. However, in the ladder's limit, which I will define in the next slide, the field theory interpretation becomes clear, as was noticed by these authors, and this is going to be our starting point. Okay, so the ladder's limit. The ladder's limit is obtained by taking the 't Hooft coupling G, so to 0, and the scalar coupling, analytically continuing it to I infinity in a particular way that we maintain, I mean, so that this combination of these factors is a constant. Now, when we do this, there's a simplification in field theory, namely only ladder-like Feynman diagrams contribute. But for our specific purposes, I mean, that's directly not important for us. For our purposes, we have two simplifications. The first is that the interpretation of the scalar insertion becomes clear as the sum of the two scalars that couple to the line. And also there is some technical simplification of the quantum spectral curve itself, which I will touch upon after some time. All right, so basically this is our starting point. What we do is we consider a cusp Wilson line with parallel insertions in the ladder's limit. Then what we do is we expand order by order in theta outside the ladder's limit, and then we manage to write down a description for the cusp Wilson line with parallel insertions for both finite phi and finite theta. Then we take both phi and theta to 0, and then we arrive on the desired defect CFT, and we can access the spectrum. Yes, so before I give you more technical details, I want to show you some results. All right, so first, let me just check how much time I have. Okay, good. I'm going all right according to plan. All right, so let's look at some results. So the first thing that we're going to consider is what we call the J is equal to 1 case. This corresponds to the insertion of one scalar. Okay, so all right, so in this case, what we can do is we can solve actually the quantum spectral curve equations analytically. That might not make too much sense right now, what I mean by that sentence, but I will explain it in the technical side of the presentation, what I exactly mean by that. But we can solve the quantum spectral curve equations analytically, and this lets us access really high loop results at weak coupling. So for example, at weak coupling, we have a 5-loop result for the insertion for the insertion of one scalar in the defect CFT. And so the first 2 loops were calculated by these authors back in the day, and we managed to calculate 3 more orders. But in my opinion, the truly non-perturbative potential of the quantum spectral curve itself is actually reached in its numerical solution. This is because by solving the quantum spectral curve numerically, we can access even finite values of the coupling, by solving the quantum spectral curve numerically, we can even access finite values of the coupling. And in particular, what we can do is we can take the coupling to finite but really high, take the coupling to be really large but also keep it finite. And what this lets us do is actually also extract strong coupling results. And so by doing this, basically we were able to extract a 4-order result at strong coupling. Again, the first 2 orders were calculated by these authors by doing the Witten diagram calculation. We managed to extend the result to 4 orders. And basically, after we published this paper, the authors of this paper contacted us and told us that actually they were also able to extract, at least from their analytic bootstrap results, the 3rd order result that we had. And they have since confirmed that they have also matched our 4th order result. So that's very good. Anyway, so these are the strong coupling results, but now it's time for what I like to call the crown jewels, the full non-perturbative spectral plot. So, so this is basically the quantum spectral curve in its full power. As we can see, we have the red lines here represents the weak coupling result. So this is our 5-loop weak coupling result. The blue line here is a 2-order strong coupling result of Jomby, Roybal, and Saitlin. And you can see that the numerical solution of the quantum spectral curve not only matches really well both the weak and strong coupling results, but it is able to access the regime of finite coupling, which is inaccessible both by perturbation theory on both sides of the ADS-CFT duality, as well as it is able to interpolate smoothly between both weak and strong coupling. And this basically means this shows that this is a really very non-trivial test of the ADS-CFT conjecture itself. And this basically was our main result. Now, as I mentioned before, we can also consider situations where the angles theta and phi are not necessarily 0. So first, we can consider the situation where phi is equal to 0. So we're still on the 1D defect CFT, but theta is not equal to 0. That means at some point, we have a change in the coupling to the scalar. So basically, we're trying to calculate the spectrum of a defect changing operator. And again, we have a non-perturbative spectral plot over here, as well as we can extract both weak coupling results at one loop, and even we can extract strong coupling results at 1 order, which matches with the analytical prediction of these people. Again, you can see that so this is the strong coupling result of these people and the weak coupling result. Same way, we can also switch on phi. Basically, we can have both phi and theta not non-zero. And in this case as well, we can do the same thing. We have a proper non-perturbative plot that interpolates very well. We have a 1-loop result at weak coupling, 1-order result at strong coupling. Everything matches previous predictions. So this is all for the j is equal to 1 case. And now I want to show you some new results. Again, this is for the j is equal to 2 case, so where we are inserting 2 scalars. Again, just like I mentioned before, we can solve the quantum spectral curve analytically at weak coupling and extract high loop results. So we have a 2-loop result. I mean, at the moment, we have a 2-loop result. It really is just a matter of patience and computing power, how many loops we get. So at the moment, we just have 2 loops. Also, we can do the same thing. We can solve the quantum spectral curve numerically. We can access finite coupling, and then we can access finite but large coupling. And from there, we can extract strong coupling results. Again, we have a 2-order strong coupling result at the moment, but yes, nothing is really stopping us from accessing more orders here. Again, we have a non-perturbative plot. In the case of j is equal to 1 insertion, the plot basically started at 1 at weak coupling and went to 2 at strong coupling. In the case of j is equal to 2, it starts at 2 at weak coupling and goes to 4 at strong coupling. So these are the main results that I have. And in the last part of my talk, I would like to present like just a brief introduction to integrability and also to this quantum spectral curve itself in just 1 second. All right, so let's begin with the story of integrability in n equals 4 supersymmetric Yang-Mills theory. It all began with a landmark paper of Minahan and Zarembo, where what the authors did was that they showed that the spectrum of a single trace of scalars has a one-to-one correspondence with the spectrum of the SO6 spin chain Hamiltonian at one loop. Okay, so what this means, to illustrate, we can consider just the SU2 sector, which is the smallest closed subsector in n equals 4 supersymmetric Yang-Mills theory, which has two complex scalars. So in this sector, we have operators of this form, z to the power L minus n1 and x to the power n1. So I mean, this would be an operator of length L. And so basically what Minahan Zarembo tells us is that a single trace operator of length L made from z's and x's can be mapped, you can make a one-to-one map between this and a state of a Heisenberg XXX spin chain of length L, where with n1 excitations, basically. All right, so we can there exists a dictionary over here. Why do we do all this? Because it turns out that the Heisenberg spin chain is integrable and can be solved using Bethe-Ansatz techniques. In particular, we can use the algebraic Bethe-Ansatz equations, and what we can do is the algebraic Bethe-Ansatz equations basically can be used to solve this model where well, okay, sorry, this is not U, this is, okay, yeah, this is U, sorry, where Ui in the beta root is related to the momentum of the magnons on the spin chain by this transformation. And basically, where we can calculate the spectrum of the Hamiltonian itself, and this spectrum and this result that we have here matches is exactly the one loop anomalous dimension of this operator. Okay, so that's how integrability works for at least the SU2 sector in n equals 4 supersymmetric Yang-Mills theory. Of course, SU2 sector is not enough. We want to include, like, we want not just to access SU2, but the full PSU2, 2/4 symmetry. In order to do this, basically, we need to increase the rank of the spin chain itself. Now, the problem that happens with the Bethe-Ansatz equations when we increase the rank of the spin chain is that you don't have a set of Bethe-Ansatz equations, but you have many sets of nested Bethe-Ansatz equations. So computationally, this becomes a big pain. Additionally, what happens is that if we go to higher loops, so all this was valid at one loop. Suppose I go to 2 loops, then the interaction in the Heisenberg spin chain, I mean, in the spin chain Hamiltonian that I get, slowly becomes more and more non-local. So for these two reasons, basically, Bethe-Ansatz techniques are a bit of a pain to work with if we try to solve anything more than the simplest problems. And so at this point, we ask ourselves, is there a workaround? Is there something else we can do? And turns out there is. So the way to see this is the following. So what one can do is one can collect all the roots of the Bethe-Ansatz equations, which basically define our state uniquely. And we can collect all these roots and form what's called a Baxter polynomial. Now, the Baxter polynomial is defined like this, where Ui are the beta roots. And this Baxter polynomial has some particular asymptotic, I mean, it has asymptotics u to the power n1, where n1 is the number of spin downs that we have here. All right. So this Baxter polynomial can be used to represent, can be used to describe the state that we were considering. But it turns out that this description is not really unique, because I made an assumption previously. I made an assumption previously that I have n1 spin down excitations in an otherwise spin up ground state. Now I could always have said that actually I have L minus n1 spin up excitations in a spin down ground state, right? Like, it corresponds to exactly the same thing. It's just a matter of choosing your ground state. And and basically, so yes, so this alternative interpretation is described by another Baxter polynomial, which has different asymptotics, which has asymptotics u to the power n2, where n2 is given by L minus n1. Now it turns out that both Q1 and Q2 are solutions of a Baxter equation. What's a Baxter equation? It is the analog of a Schrodinger equation that all integrable models satisfy. Okay, so I'll tell you in a moment why. I mean, it will become clear why I told you about all of this in a moment. Let's just have a look first at the Baxter equation itself for this particular spin chain. It's the Baxter equation is of this form. So it's a finite difference equation, and it is of this form where Tu is a polynomial that plays the role of the potential. The important point here is that Tu itself is only partially determined, and it is totally fixed by imposing self-consistency of the Baxter equation itself. And both Q1 and Q2, as I said in the previous slide, are linearly independent solutions of this Baxter equation. Because they are linearly independent, they satisfy a particular Wronskian relation given by this. So, okay, with all this information, what we can do is we can reverse the logic. So what we say is that we demand that Q1 and Q2 are solutions of a Baxter equation, and two, we impose that Tu is a polynomial. And it turns out that these two pieces of information are sufficient, are basically enough to imply the beta-ansatz equations themselves. So what we can do basically is bypass the entire beta-ansatz by reversing the logic and solving Baxter equations instead. All right, and this is basically the philosophy for the quantum spectral curve. One second before I move on, are people sending questions in the chat or something? I'm unable to see any questions, but if there are no questions, I'll move on. Like I couldn't see any questions in the chat. I don't think I can see the chat at all.
So, chat, Julius, will let you know if somebody wants to ask a question.
Okay, all right, great. Okay, sorry. Thank you. All right, so as I said, this implies the beta-ansatz equations. So this is basically the philosophy for the quantum spectral curve itself. Now, obviously, it's a bit more complicated than just a spin chain. The first thing is that we don't have SU2 anymore. We have PSU2 2,2/4. So we don't have 2 Q functions. We have 2 to the power 8 Q functions. Well, okay, actually, in that case, we had 4 Q functions, but whatever. So instead of having 4 Q functions, we have 2 to the power 8 Q functions. But the one lucky thing, I mean, there are many lucky things here, but one of the lucky things is that we just need 8 Q functions, which we call 4 of which we call PA. A goes from 1 to 4, and other 4 we call QI. I goes from 1 to 4, which are sort of basis functions, and functional relations amongst these 8 functions can be used to calculate all the other 256 functions. So that's one piece of good luck. And the second thing is the surprising simplicity that we have. Like in the previous case, obviously we had Baxter polynomials. In this case, we don't have polynomials anymore, we have functions, but it turns out that these aren't super complicated functions. They are complicated functions, but they are functions that have only one branch cut between -2g and 2g, and where g is the 't Hooft coupling. So all the information about the coupling is contained in this branch cut description, basically. All right. So what is the quantum spectral curve? The quantum spectral curve is basically a Riemann-Hilbert problem that can be set up with the following input of information. First is the asymptotic information. So just like in the previous case, we had this u to the power n1 and u to the power n2. The asymptotics of the Q functions of the quantum spectral curve contain the charges of the state. In particular, we are going to be studying the spectrum of scalar insertions in this defect CFT. So the quantum spectral curve will contain the scaling dimension in its asymptotics. Secondly, in the previous case, we had this polynomiality assumption of the TU of the potential. Obviously, it's a bit more complicated here. What we have are some linear monodromy equations across a branch cut, and these are called gluing conditions. Okay, and finally, we have functional relations called QQ relations. These are the same relations that let us calculate all 256 Q functions using just 8 initial functions. And these are the analog of the Wronskian relation that we had for the spin chain case. So with these three sets of input, what we can do is we can set up a Riemann-Hilbert problem, solve the Riemann-Hilbert problem, and calculate the Q functions. And from the asymptotics of the Q functions, we can extract non-perturbative information about the charges of our state. In particular, we can extract the conformal dimension for our specific case. But okay, so all of this was about single trace operators. What about the Cusp-Wilson line? So,
Julius, just before you go on, we've got a question.
yes.
So the question from Alessandro: can you describe the new asymptotic behavior in more detail? I don't know, Alessandro, whether you wanted to ask that in person.
So what was the question? Can I describe the asymptotic behavior in more detail? Was that the question?
Yes.
Okay. Yes, I will. I mean, I'll give you the explicit asymptotics of the Q functions. I think either in the in the next slide. So hopefully that will be sufficient. But if not at that point, please ask me further questions about this. So I will get to it in a moment. Are there any other questions? All right. If not, let me carry on. So as I was saying, what was I saying? That yes, so single trace so all this description works for single trace operators. What about the cusp? Now it was shown by these authors that actually a Cusp-Wilson line with L scalar insertions corresponds in a very similar way to Minahan-Zarembo to an open spin chain with boundary conditions provided by the Wilson lines themselves. Now, the thing is that integrability techniques were hitherto thought to work only for the case of orthogonal insertions. So where these L operator insertions are orthogonal insertions. However, when these authors were studying basically a cusped Wilson line in the ladder's limit, they observed that the solutions of the Baxter equation that describes this cusped Wilson line contained excited states. Okay, and they interpreted and showed as well that these excited states basically corresponded to actually making parallel insertions at the cusp in the ladder's limit. So in our description, we start from their result and we expand order by order in theta outside ladder's limit and basically expand this integrability construction for finite values of theta and phi. So we bring the parallel insertions into the purview of integrability by doing this. Then we take theta and phi to 0. Then we take theta and phi to 0 and obtain our desired state. So in the last 2 slides, I just want to show you. I want to give you a quick a schematic description of how actually this works. So, all right. Hopefully, this answers the question that I had earlier about the asymptotic information. So, as you can see, so this is what we found. So for the 4 P functions, we have the following asymptotics that are given here. So we have some fractional power of the spectral parameter, and then we have an asymptotic expansion. The coefficient of the leading power can be expressed in terms of the conformal dimension itself. For the Q functions, we see that we not only have a fractional power, but also we have the conformal dimension itself as part of the asymptotics. Again, the leading coefficient can be expressed in terms of the conformal dimension itself. And what we can do now is also write an asymptotic series for these P and Q functions in terms of some coefficients CAN, A going from 1 to 4 for the P functions, and DAN, DIN, I going from 1 to 4 for the Q function. Yes, and in the numerical optimization problem that we're going to set up, basically what we're going to be playing with are going to be delta and all of these C's, and at the and when we find the minimum of the objective function, basically we will end up with the correct value of delta, which will give us the desired spectrum. Yes, so for the person who asked the question, was this what you wanted with the asymptotic information? Okay, I'll assume that as a yes and move on. Again, feel free to ask me more about this. Anyway, I'm going to be done quite soon, so there will be enough time for further questions in this direction. All right, so what do we have? We have now, as I described a couple of slides ago, we need 3 pieces of information to make the quantum spectral curve work. The first piece of information is the asymptotics, which I've displayed to you right now. So the asymptotics brings in basically all these parameters into the game. So the CAN, the parameters of the expansion of the P functions, and delta itself, which corresponds to the conformal dimension. So now we have all these parameters in the game. We have the asymptotics. So now we move to step 2. So the next piece of information that we need for this Riemann-Hilbert problem is are the functional relations amongst these P and Q functions themselves. I mean, there are a lot of them, but for our purposes, these 3 are going to suffice. Let me first just talk about the first relation. Now, the first relation, basically, in addition to the P and Q functions, as I said, there's a family of 256 functions, and 16 of those functions are called QAI, A going from 1 to 4 and I going from 1 to 4. So these basically are very similar to the functions that we had in the Wronskian, right? In the previous slide with the Wronskian, we had this Q12. So exactly like this, we have QAI over here. And these are some auxiliary functions. The reason we bring them in is because it will, I mean, you'll see, I'll explain why we bring these auxiliary functions in, but they are useful for us. The other QQ relation that we need basically tells us how to translate between P and Q if we know QAI and P. So this is good because this now lets us just solve for the CAN and delta. We don't have to solve for C, D, and delta. We can just solve for C and delta. And finally, we need another relation which basically computes the analytic continuation of the P and the Q functions through the branch cut and shows us how to compare them. Now, obviously, the reason we need this is because finally, when we set up our optimization problem, what we are going to do is we're going to compute the QI numerically on 2 sides of the branch cut. Then we're going to, numerically, we're going to compute in terms of our parameters CAN and delta on 2 sides of the branch cut. Then we're going to impose these gluing conditions, these linear monodromy conditions through the branch cut. And that is going to basically be our objective function, which we will minimize and finally fix delta and C. So this is why we need the second and third relation. All right. So how do we go about actually solving the quantum spectral curve numerically? The first thing we're going to do is we're going to parameterize the P functions in terms of a Zhukovsky variable. Now, the reason there are 2 advantages of doing this. The first thing is that it makes the series of P a convergent series rather than an asymptotic series, because I'm including the coupling in the Zhukovsky variable itself. The next step that we're going to do is we're going to expand at large imaginary U. We're going to expand this relation at large imaginary U. Now, what happens when we do this is that the left-hand side basically becomes a derivative operator, And so we get a well-defined linear problem, and we can asymptotically we can solve. So asymptotically we get a well-defined linear problem, and we can solve this and basically parameterize the functions qai in terms of delta and can asymptotically. Then what we can do is recursively use the same QQ relation. As you can see, we can just I can actually just use this QQ relation to bring down the argument of QAI by a factor of I/2. So I can use it recursively and basically bring down the argument of QAI until I more or less reach the branch cut. So as I approach the real axis, so I approach the branch cut on the real axis. And at this point, because the series in P is convergent, and QAI will take me recursively to the asymptotic region where QAI is also precise, I can compute the Qs at the branch cut using this function. Now, the next thing that I need to do is compute the Q tildes, which are the analytically continued Qs. Now, it turns out that this is not very difficult to do. Again, because of the Zhukovsky parameterization, all we need to do is take x of u to 1 over x of u, and we can obtain, so this basically obtains P tilde A. We use this relation to calculate Q tilde. So now we have Q and Q tilde calculated at the branch cut. We know the gluing conditions. I haven't displayed the gluing conditions here right now, but the gluing conditions are just some linear, conditions. It's just a linear transformation between Q1, Q2, Q3, Q4, and Q tilde 1, Q tilde 2, Q tilde 3, and Q tilde 4. So we just impose that this gluing condition is satisfied and use this to define an objective function, and we optimize the objective function. And once we optimize the objective function, we use these parameters delta and can to optimize the objective function, and at the optimal point, we can basically calculate the numerical value of delta, which was what we set out to do, and basically we are done at this point. Okay, so this is a brief description of how the numerical solution of the quantum spectral curve works. And in particular, it can be used to calculate the spectrum of the 1D defect CFT. So let me make a quick summary of what we have done, and also throw some light on some open questions. All right, so what we have done firstly is successfully applied the quantum spectral curve to study parallel insertions of parallel scalars. So thereby we have expanded the integrability construction for the setup. And in the limit that we take both the cusp angles to 0, if we had not any parallel insertions, then in the limit that we take the cusp angle to 0, basically what happens is we end up with an infinite straight Wilson line, which is half BPS. So the ground state, so to say, trivializes. But if we start with parallel insertions and then take both the angles to 0, then we can actually access the defect CFT itself. And so what we were able to do was able to find the first two excited states. We were able to either match with or extend or even obtain new analytical weak and strong coupling data. Some open questions, some future directions now. It seems to us, so if you looked at the weak coupling result for the j is equal to 2 case, there was some square roots of 5 here and there. So this suggests to us that maybe there is a second state with the opposite sign of the square root. So, the hunt is on for this state. What about states at higher j? J is equal to 3, 4. I got actually very excited last week where I almost found the j is equal to 3 states. So I was hoping my numerics would converge and I could show you j is equal to 3 today, but unfortunately it hasn't happened as fast. Anyway, another thing that could be done is take the number of states j very high and then try to write some asymptotic beta ansatz equations for this setup. Also, the 1D defect CFT itself is a nice playground for one to study not just the spectrum, but also structure constants. So also the 3-point function, there has been a lot of recent results and ideas in the direction that suggest that the Q functions of the quantum spectral curve themselves contain also information about the structure constants. So that's a direction to pursue. And finally, the non-supersymmetric Wilson loop, or like the Wilson loop, the proper Wilson loop. Now, it was shown recently by a group in Argentina that at one loop at least, the non-supersymmetric Wilson loop in n equals 4 supersymmetric Yang-Mills theory, the non-supersymmetric Wilson loop is integrable at one loop. So does the integrability construction persist at higher loops? Can we write a quantum spectral curve description for it? These are some open questions that that one could consider. Anyway, that brings me to the end of my presentation, and I would like to thank everyone for their attention.
Okay, so thank you very much.
Thank you.
All right, so we've got some time for some questions. Perhaps we can start. So Alessandro did try to talk